Recording. All right. Hi, everyone. This is the second stream of working on a Casio Loopy emulator. So far, we haven't really done a lot. I'll talk a little bit about what this project is all about first, and then we'll sort of talk a little bit about what I did last time, and some plans for what I might do in the future. So, first off, Casio Loopy. It's a system that I never even heard of until actually maybe a month ago when Rachel Weil told me about it at NodeConf Europe, and just sounded really cool. Game system that basically nobody has done much of an emulation effort for. So there's a little bit done in MAME, but seems like that process is sort of stalled out. So I thought, oh, it'd be kind of fun to, like, you know, try and work on something like that. Fun little project. So there's not a lot of information about the system. As a result, a lot of this is going to be like just sort of digging in and trying to figure out what's going on with the system, like how does stuff work. Some of the work might be just like looking at a ROM and trying to figure out like what part is the graphics, what part is the sound, you know. So yeah, it might get a little bit hairy at times, but yeah, that's kind of the fun of this. So I'm mostly a programmer, so I'm going to focus a lot on the code parts of it. So there probably won't be any pretty pictures for a while, but yeah, I guess just to sort of start us off, like let's take a look at a little bit about, whoops, I don't want to do this. Casio Loopy. Let's just take a look at what the system looks like. It's from 1995. Oh, look at this. Ask to pay. Okay, so it's from 1995. Cartridge-based systems, 32-bit. It's actually apparently very much similar to kind of like the Sega 32X. Uses the same CPU. Graphics are a little bit different. Anyway, if you're curious about it, there's like some interesting YouTube videos that you can sort of look and see what the games look like. One of the really cool things about it is it has a printer, so you can like generate images in the games and then like print them out. And I've never seen this, but it would be very cool to take a look at some of that. So what we were working on before was basically just being able to take a ROM. So I have this ROM here that's called anime.bin. It's for this game called Anime World, I believe. Anime Land, Anime Rando. So what we had before was the basics of a project here. We can run make and we'll build a little bit, and then we can run this project here, and we have it like hard coded to load our file. And all it's doing right now is disassembling the file. So you can see that like we're starting at offset 480 in the file, and we're just disassembling like instructions here. So move A, this is one of the instructions. Word here is basically when we tried to disassemble it and we basically couldn't find an instruction. So the way I'm trying to determine whether or not we have an instruction or not, we're basically looking at this online disassembler. So it knows how to disassemble Super H2 CPU instructions. And so what I did before was I just copied a bunch of instructions in here, and then I sort of relying on its disassembler to do the right job. And so then we also have this document here, which is a document about the Super H system. And I'm just going through here and looking at what it says about all the instructions. So disassembling is like kind of the simplest part. Once we have everything disassembled and we feel pretty good about that, then we can move on to actually writing an emulator of the various instructions. So, so that's what I'm going to do now. Let's take a look at where we were at. If I remember correctly, we were basically disassembling a bunch of instructions and then just waiting to see if any of them blow up. So in the previous stream, I was reading like 512 instructions and then just printing them out, and whatever didn't work, then I would implement. So we basically had 512 working. As you can see, like it's printing out everything here and nothing is blowing up. If it did blow up, it would basically have an assert, this assert 0 at the bottom. So I'm just going to double this again and see if we blow up on anything. So actually, let's make it and build it. Okay, so we got another assertion failed. So this is basically the same thing we were doing last time, just taking a look at what it got here and then seeing if this is a real instruction. So previously I was actually copying in a big chunk of code and then into the disassembler here and then trying to see. But now I'm actually kind of wondering if maybe it's just simpler to copy this one instruction and just see what it says. So we can type it in here, and yeah, this is way simpler actually. I should have done this last time. We can just type this in here, and yeah, just so you can see, like if I type in 600D, this should give me the same instruction here. So this says it's XUWR0R0, and great, that's the same thing that ours is saying. So that's just sort of a sign that like we're going in the right direction here. So yeah, anyway, so we were at C801, so we'll put that back in here. And we get test number 1 R0. So we know it's a test instruction. So the steps that I was going through before, this is like an instruction list here. And this one is like grouped by category, but it's actually way simpler for us in our case if we just look at the instruction sets in alphabetical order. So we'll just go through, and here's our test, and we're looking for a test number. I hope you can all see this. I don't know, it's pretty small. I can try and blow it up a little bit. Yeah, that's a little better. I can tell because it was a little small for me, so. So this looks like the one we're looking at here, I think. Again, we also were printing out the bits for the instructions, so we can kind of look at this bit pattern here and just see whether or not it matches up. So C801, so C is 1100, there's our 8, and so then the bottom bits are our immediate values. So okay, so that's basically what we want to try and implement now. So we'll go back to our code, and what we were doing here in our disassemble or decode function here is we look at the top 4 bits because it looks like those are the bits that basically tell us what type of instruction that we're going to look at. Like you can basically branch off of those and then determine what kind of instruction it is. And a lot of them seem to actually be grouped in that way, which is very convenient. It's probably just because it's easier to decode in hardware, but it also is easier for us to code too. So here's our OXC. This is the top 4 bits here. And then the next bits we were looking at are 8. So we already had a case where we were looking and the next 4 bits were a 1. So I'm just going to copy this case here, whoops, and then change that to an 8. And again, the instruction is test number, and then it looks like, yeah, R0. So we can just change our message here, test, and then number, and the number, so this is actually our immediate value here, so it doesn't get multiplied. And there's R0. And so then if we rebuild this, turn this back to an immediate. Okay, it went too far. I think we probably missed it. So let's grep for our C801. There it is. So we're getting a test and an R0. So that looks pretty good. And you can see that was at 89C. So let's see, 89C. So that was way back here. So we actually, we churned through a bunch of other code here. So one of the things that we mentioned last time that was like a little bit annoying about the way I'm doing the decoding is that currently there are a number of instructions that we just don't know what to do with, and so we print out word. Partially because there's a lot of instructions that are just invalid. But some of these are valid, and it's not clear like immediately which ones are and which ones aren't. So I just want to make sure that like none of these are. It'd be nice actually if I had like a little marker to sort of show like which ones I've already looked at, but maybe I'll just have to remember the address here. So I'm pretty sure everything above this FF we already looked at. Oh, actually, let's see. We can actually check we already did this many. We were at 512, right? So that should be 680 is where we were before last time. So that means that basically everything after 680 here we should probably take a quick look at. So I'm actually just going to copy these into the online disassembler just like we did before and just make sure that these don't actually map to anything. So 01C0. Yep, nothing. And then zeros I know is nothing. FEDC, that might be something, but probably not. Oops. Nope, nothing. And 0540. Actually, 00C0. Let's look at that one. Nope. Okay. 0540. So yeah, this is kind of tedious, but it turns out a lot of working on an emulator is actually kind of tedious. So yeah, that one looks good too. Like the exciting part is when everything sort of comes together at the end. I guess that's like a lot of projects. Things kind of come together at the end. So 100. Let's see, 09A. Yep, nothing. And also, if you notice that I'm like making a mistake, please tell me, because I would love to have people save me sometime. So E100, that's not really a word. 45D0, that's right. Yeah. So these are all good. So we can remember now that 8FA is basically like we're good up to there. So yeah, let's just write it down because I'm totally gonna forget otherwise. 8FA, FA. Yep. Okay. Cool. I don't know if I want to waste that much space, but whatever. Okay. So now going back to where we were hitting that assert. Yeah, so we're hitting it at CB100. So let's look at CB100 now. That says it's an OR instruction. So, all right, let's take a look at that. OR instruction. Okay, there's our OR B. We probably want this one, or immediate. Is that right? Or immediate, yeah. Oh, and so yeah, this number sign means it's an immediate value. It's like stored in the instruction itself. So that's what these like bits down here mean, these I values. That's the immediate value. And so this is a 32-bit machine. So this value can only be an 8-bit value. Yeah, an 8-bit value. The instructions are only 16 bits, and so what you'll we kind of talked about this before, but like what you'll see is that a lot of these instructions are basically just building up 32-bit values by like combining things together. So so yeah, the top bits are C, and then the next after that is D, right? Just to make sure. Oh, B, right? Sorry, is that right? Yeah, A plus 1, right? Okay, so now we're doing CB, so that's actually right by what we were already looking at. And you can see, like, oh, we have a 700 here, so I'm actually going to just satisfy my desire to keep things sorted. So you can already see here, again, like, there's a clear pattern coming here. Like, if it's a C, it looks like we look at the next 4 bits, and that's going to give us the structure of the instruction. So, yeah, what was I looking at again? This is OR immediate. So, and actually it has a very similar structure to test, which we just did. And yeah, it looks like it's always on R0. So we'll do a bit make, oops, fix that, okay. Looks like we got a bunch more words here, so we should probably take a look at that. But actually, I want to make sure that we got our OR. So that's, well, I saw one here. Is that the one we were looking at before? I really need to keep track of this. Yeah, let's just grep for OR. Yeah, that's probably this one. Yeah, okay, cool. So, so that looks good. That looks like the same as what we were getting in the other one. So, but now you can also see that we got a bunch more words. So I'm just gonna look at these here, and we were looking at O, 8FA. FA. So that we've got before. So now we've got these ones to check out. So let's look at 400E. 400E. Ooh, this is one. Okay. So yeah, this is why I did it, because if I don't do this, then, and actually this is what happened in the last stream too. I was like, oh man, I totally disassembled like 500 instructions, and then I had to like go back and fill in these ones afterwards because I totally skipped them. So better to just go through and do it this way. So let's see. LDC R0SR, LDC R0SR. So that's this one here. It looks like it's a top 4 bits, and then the bottom bits are 0E. Is that right? 0E? Where'd it go? Yeah, 40E. Okay, cool. So we'll look at 4. That's back up here. It's funny, programming on this screen is like, because my laptop is a Retina screen, but my monitor isn't, like, it's kind of crazy. Everything, like, I have to scale up on my laptop, but then don't scale on my, I don't know, it's hard to explain, but it's like, it's scaling on my monitor too, and so everything is enormous. I feel like, yeah, I mean, it's nice, it's really easy to read, I guess, but I also don't see as much stuff. So LDC, and so we're doing LDCR, this one, SR. Yeah, I think that's right. And LDC RMSR. Yep. That's weird. T-bit. Oh yeah, okay. So this is interesting. It actually is saying that it sets the T-bit as well. The T-bit is basically, I guess on this processor, like a lot of 8-bit processors, like if you've ever programmed on well, if you know anything about like the 6502, which is the kind of like the chip in the NES, or like the Z80, Z80, whatever you call it. A lot of those have a flag register where they sort of have a collection of bits that they store. The way this one seems to work is that they have specific instructions that set 1 bit, and then you can check that 1 bit, and that's all it is. So it's like much simpler than a flag register. So if you've ever worked on an emulator before, you know that like the flags bits are kind of like the most annoying thing to do, because they're like not really super well specified, or they're well specified, but like they're just complicated to compute a lot of times. And so this is like way simpler, which is very cool. So yeah, let's see, there's our SR, and I think that's good. So I'm going to grep for LDC here just to make sure we get it. So there we go. Yeah, it looks good. All right. I hope everyone's been having a good day today. It's so quiet in the chat room. I feel like I'm talking to myself. Maybe I am. Maybe you are all bots. No, it's all right. You're not bots. You're real people, I'm sure. Okay. Yeah. So we were looking at oh, so we lost that one because we beep boop beep. Yeah. That's exactly what the bots would say. So yeah, we lost that one we were looking at before, 400E. So now we're looking at 0101. Let's see if that is anything. Nope. And then 80. We probably already looked at that one. Yeah. And then FF0F. So FF0F. Is that what I said? Yeah. I'm writing this all in C, so like a lot of the nice features that people would use, I can't really use. I might switch to C++ at some point, but for now I'm just going to stick with C because I like C, like a weirdo. But what that means is, did I type that right? Oh, 5FF? Oh yeah, we got a Mackle. Is that really the instruction? This seems like a super weird instruction. I just have to say. I don't know exactly what this is, but like the fact that it's doing an R15 plus and an R5 plus, and this @ symbol means that it's doing a memory read there too, I think. This just seems like the type of instruction that's like you're probably not actually executing. So my guess is that this is actually data and it just happens to be an instruction. But we'll do it anyway because, you know, we want all the instructions to work. So let's find it here. We're looking for Mackle. Oh, it's right here. Mackle. Oh yeah, okay. Oh, interesting. Okay. So Mackle, I think, is like a multiply accumulate. Is this what this is? Let's just take a look because I'm kind of curious. Yeah, multiply and accumulate long. So this is an instruction that's basically like, it's a multiply add. It like multiplies two numbers and then adds it with the previous result. So yeah, so maybe they actually are doing this for real, and I was wrong. I was wrong to doubt them. In any case, we'll write it up. Where'd it go? Mackle. And so this has got all weird stuff on it. Oh, interesting. Okay. So this is saying it's an SH2 instruction. So that really does make it a little bit clearer that maybe this is an SH2. I wasn't sure because the Wikipedia page says it's an SH1, which is like an older version of the same chip. So, yeah, so let's put that in. Again, we're looking for 05. So we have our 0 section here, and then we're looking for, let's say, 5 in the, 5 in the, oh no, we're just looking for F in the bottom bits. Yeah. So again, this one looks like it actually is doing the same thing. A lot of them are looking at the bottom bits. You can tell I'm just masking off the bottom bits here, and then I'm checking for a certain value. So I'm just gonna do the same thing here. And we have NM. So we've got MN. Yeah, looks good. And let's just do Mackle. The L means long. That's the size of the instruction. Basically, it means that it's using 32-bit instructions. So RM, and there's our M and there's our N. So let's just make sure we've got our Mackle. Yeah, R15, R5. If we go back to here, R15, R5. Yeah, looks good. Looks good. All right, cool. So let's go back and make sure that we didn't miss any. FF0F, we know that one wasn't. FF48. FF48. I'm thinking these FFs are never going to be any, but I don't know. And then there's our 0. Okay, so now we're up to 0950, so I'm just going to write that here. 950. And then see where we're blowing up. We blow up on 6AC0. 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 Move B. So this is moving a byte. Interestingly, it looks like it's... so this is one of these architectures where it's kind of annoying. It's hard to tell if a move is reading or writing. But I think this is saying that it's reading from the address at R12 and then writing into R10. But we can actually look at the data sheet to see what it says that's going to do. I have this here because I want to add color later. So maybe after we do a few more instructions, I'll add some color to make it look like a little less boring here. I always forget the commands to like to make it so that it prints color in Linux. So being able to just like look at a place where I've already done it is nice. Okay, so yeah, move B, and we're looking at a 6. We'll find that here. our move B. So there's a bunch of different move Bs. The one we're looking for, I think, is this one. Just make sure that's a 6 and that's a 0. And there's our 6 and there's our 0. So, yep, we'll do that. Go back to our code. Oops. We'll go back down to our 6. So yeah, the code here is like looking pretty nasty, but sort of my philosophy is like write nasty code, and then once you sort of know what you're actually going to do, then you can write nicer code. You can like clean it up. And I don't know, some of that maybe I'll do on stream, some maybe I'll just do off stream. Kind of depends on what people think is interesting about watching a dude work on an emulator. So there's our move B. Yeah, oh, and right, see, this is one cool thing too. We've got our 0, 1, 2, and then it's BWL, so that's byte word long, so 1 byte, 2 bytes, 4 bytes. So then I bet you we have, yeah, and there's our BWL as well. So if we make and run, and we look for our mov B, the one we were just looking at was this one. Yeah, so it looks like it got decoded properly, and it decoded a bunch more. And again, we're going to have to take a look at our words and just make sure that we didn't miss any. And so yeah, you can see right here, there's a ton, 950. See, we're all the way back here. So yeah, I really wish there was like a nicer way to like just know right away if these were invalid or not. Honestly, it might just be one of these things where it's like you just do it once and then you never think about it again. It might be actually what I could do is yeah, I could do something smart, like use the computer and have it help me do this, which is basically yeah, I'm gonna do something, okay, well, smart, quote unquote smart. I'm gonna do something really stupid actually, which is I'm just gonna make a giant array, which is words that we found. Giant. This is really not that big of an array, honestly, like 65K, whatever. And then anytime we get to a case where it's a printf word, which is always going to be in here, we're just going to do printf word, and we're going to write the instruction in here. Yeah, so it looks good. And then at the end, oh, so we're still doing this assert. So what I'm going to do is turn this into a function so I can put it before the assert. I'm just going to write a function that's like print words. And then we're just going to loop through every single so 65536 is the number of possible instructions, because there are to the 16th, and that's what that is. So I'm just going to say if gwords I equals 1, that's what I called it, right? Yep. Then printf words word. Actually, yeah, why not? Well, I want it to be a little bit easier to read than that, so we'll see what it is. This is what, 8x? No, 4x. Yeah. And this should just be I, actually. And then we can do print words. And then down here, in case we actually make it all the way through, we can do print words there too. So let's just run. Yeah, so here's all our words, and let's put a printf like this, and then do printf words. This can all be one printf. Yeah, there's our words. Oh, yeah. Hi, Pi a la mode. Py a la mode. Yeah, so the problem is here is that this is writing to std error, and these are all writing to std out. So I'm just gonna cheat and also write to std error, and that'll make it so that yeah, so then we get our list like before. And then if I mod, let's see, I plus 1 mod 16 0. So this is just to make it so that we get some new what? Oh, right. No, we want like a count. And we'll bump our count here. There we go. What is going on here? That's pretty weird. Oh, so that's our stood out. So the other thing I'm going to do is I'm going to do a flush on stood out, just so that yeah, okay. So this is like where we blew up, and then here's all our words, and then finally we'll just print out a couple more of these. Okay, cool. So this is the list of all of the words in order, and now what we can do is just like have a whitelist, or no, a list. Basically, a list of the stuff that we know are okay, are invalid. So we'll just do this, and we know that like we already checked 0. So then what I'll do is I'll just say and yeah, and again, I'm just going to do this like the dumbest way. So we'll just do this less than, and so I actually want the list of the size of this. So I'm just going to do size t invalid equals size of invalid divided size of invalid 0. This is a classic C trick to getting a list of an array, or the length of an array. You end up having to do a lot of this kind of dumb stuff when you're writing C. So if invalid j equals I, then we're just gonna continue. So this is our this, and then we'll do I don't think I have a bool. I'll add one later. Is known invalid, and we'll pass in inster, and we'll do this and say return 1, return 0. Say if is known invalid I, then continue. So that should currently remove 0 from the list, I think, once I fix all this stuff. So this should be G, and this should be G2, and num invalid should be G num invalid. This is all just like ugly hacks, but you know. And this is J. And it doesn't like that I'm comparing G invalid, which is an int. So I'll just change this to uint16t. There we go. And then we get nothing. Okay. Is known invalid. If is known invalid, what did I do wrong? Whoops. This should be that, right? There we go. But we didn't actually remove 0. Why not? If G invalid J equals, oh, equals inster. Okay, there we go. So now we actually removed 0 from our list. So now we can go back and rep our word list, and we know that we know what do we know? We know a bunch of these are like actually not valid. So I'm just gonna write. Let's see. I kind of want to just pull these into a list based on Or should I do it? Okay. Okay, why not? So we'll do the same thing here. We'll do, what I want to look for is basically, what? Which ones we've already looked at. Yeah, right. This is all like super hacks, by the way, everyone. I'm sorry. But this is like, I don't know. After being at work and not getting to do ugly hacks like this is like, it's kind of fun, right? So we're looking at our address. Our address is address. Yeah. And we know that we're less than 0950. Then we already looked at it. And then what I'm going to do is inside print words, I'm going to just change this G words to G looked at. And then this should be, and actually then get rid of our, this. Okay, so these should be the ones that we already looked at, I think, if I wrote this code right. Were people paying attention? Did I do it right? I don't know. Okay, but in any case, we'll assume that this works. So I'm going to copy this over here and then just paste it. And actually, you know what I want to do? I want to write an OX in front of this so that I don't have to do anything. Yeah, okay, there's our list. And there's our paste. I'll format it, whoops, like so. And yeah, now we've got our list. So yeah, like I said, I'm going to assume that this is right until proven otherwise. And I'm going to, yeah, I guess I'll leave this in here for now because it doesn't really hurt anything. But I want to change our print words back to printing G words. And then I also want to change this back to not printing known invalids. So, okay, so these ones should be the ones we haven't looked at yet, I think. And just to see if that makes sense, let's look at 201. Where's 201? Yeah, see, and this is OA. Okay, cool. So I think the totally hacked up code that I just wrote actually works, which is always, cool. And it's also really cool when you're writing on stream and everybody is watching you. Let's see. So let's take a look at these instructions then and see if they're real or not. And then once we do, then we can add them to our list, and then now we can just use this for to determine whether or not we actually have to check something, which is so much nicer. That's not it. That's my Twitch. I can't paste. Okay, 0201. In fact, actually, I can just copy this in here. Will this work? Maybe it will work, because that would be really cool. Because then, will you do it? That's so annoying. Okay, so what we're gonna do is we're gonna format this back to this with no comma, because I'm pretty sure this will work. And then maybe I'll just like hack this up. Yeah. Okay. See, and this is very cool. See, optimizing my workflow. So now I can basically take these guys here and add them to the list. Really do wish that I could do this without having to do it manually, but maybe it's annoying that the, oh my goodness, what happened there? There we go. Yeah, it's annoying that they like they want different formats. Yeah, so then it removed those from our list. The other ones were these ones here, starting at this and going to this. What I should do is write a little macro for this. Cool. And just make sure. Yep. Okay. And then forward 444 and these two. Let's see. Wait, did that one show up twice? Why is it? Oh no, I see. That one. There we go. I should make that jump to the next value, but it's okay for now. Okay, so then we should just get the ones that we need to implement, which are these three, and just to be sure, we'll drop that in here, and that should be real instructions. Yes. Okay. So, let's do these. Let's do these. I have a feeling that we're going to be able to make it through all of the instructions tonight. We'll see, right? So this one's 089C, and it's a move B. So it's a move B, but it's using this syntax here. This syntax means it's indirect, but it's also got a it reads from this address, but it's also got a displacement. So it kind of, I think it adds these two together, and then it reads the value. So we've got move B. Where was I? Right here. So I think that's this one. 0 and C. Is that right? 0 and C. Yep. Okay. Yeah. So we'll go back to our 0 here. 0 and C. Oh, looks like we have another one out of order. Oh, no, this one's looking at the bottom 8 bits. So we'll look at C here. And we know that this is a move B. Oops. Move B. Indirected from these two registers. Actually, it has 3 registers. 3 registers. Where did that one go again? This one. Yeah, so... Oh, it's always R0. It's always R0. So, and then it's MN. MN. Yeah. Like this, I think. I'm just going to make sure I did that right. 089C. Oh, that's funny. We already had an 089C. Oh yeah, that's wrong. There's no at there. So this probably seems kind of pointless, but the reason we're writing a disassembler is that to actually be able to sort of know what's going on, we're going to need to be able to know what the instructions are. Before you can actually implement any of the instructions, it's like super useful to be able to at least look at them and see what the values are. So yeah. Okay, yeah, that looks good. So I kind of want to factor this out, but I think I'm gonna wait to do that a little bit later. Let's go back to our list of instructions. OF36. So I'm guessing this is another one where it's O and the bottom is 6. We'll take a look. So this is O, and we know it's a move L. So O and 6. Nope, that's not it. O and 6. Nope. O and 6, this one. And I'll double click so I can see it. Yep, okay. So this is basically the same as the other instruction except for it's on the other side. It basically reads from this register, yeah, and then writes to this address in memory. So we'll take a look at that. R0 plus Rn. Yeah. And yeah, so it's got 6 on the bottom. Move L. Oh, that's funny. Yeah, it's basically the same as this instruction here, only it's an L instead of a W. So we already had that one ready to go. Okay, so then the last one is this 8D0C, this BTS. So BT is, I think, it's a branch of some kind, although I can't actually remember what the T means. Honestly, it doesn't really matter at this point because we're just writing a disassembler. So, oh, they call this BT.S and this calls it BT/S. I'm going to use the CPU nomenclature instead. So yeah, this has a top of 8, and then that's D, right? Yeah, 8D, and then the 0C is the displacement, basically how far to jump. So we'll look at that. So we already have some 8s in here, I bet. Yeah, so here's our 8, and then we're looking at D. So we'll do a D here. So yeah, this is another one where I think I might actually just factor it out because it looks like they're all going to have the same structure, BT/S. And then it says displacement times 2, which is what I'm doing here. Plus PC, yeah. So this looks fine. So BT. There's our BTS. They say 20. We say 18. Interesting. Did we do it wrong? Dis2 plus PC. I think this might just be because, yeah, I think this is another one of these situations where it's actually adding in PC for us. Although if that's true, why is this 18? Should be bigger. We'll take a look at that again later. I'm not too concerned about it because considering we don't really have a PC. We're going to want to switch this over to actually using the real PC at some point, but this is just going to be sort of what you'd call like a static disassembler. So like without having any knowledge of what the system is actually doing. We're going to not want to have much static disassembly, but for now it's like good for sort of understanding what the system is doing. So I'm going to pull this part out here. It's not really saving us much. All right, I'll wait. Core dump. Oh yeah, and so then, yeah, so we can see no words here, which means that all the words that we saw are words that we know are not actually valid instructions because we checked them, which is, again, very cool. So it did abort, though. It aborted on this instruction, which is a real instruction. We'll just copy it in, T2AB, and that's an OR of 2 registers. So we'll look at that one here. OR of 2 registers, and it's got a high of 2 and a low of B, 2B, yeah. Again, I'm just like looking at the patterns here, and I'm just seeing what the pattern is, and then I'm like literally just copying the pattern into the code here. So there's our 2, and actually we want that, and this is, whoops, OXB, and we know this is an OR of 2 registers. And so you can see, like, yeah, we've got a test and OR. We could probably actually just go through the instructions at this point and like fill in the blanks. But I think I said this before, but like I kind of like actually just using the actual code to determine what to implement, because there's tons of instructions that probably never get used. And like, why would we bother with those until we need to, right? Okay, 63DF. X to S. So this is a sign extension operator. Sign extension. Sign extension. X to S. Yeah. 6F. 6F. Yeah, looks good. So we'll go back to our 6F. And we know this is sign extension. That's my tea kettle telling me that it's turning off the heat. I think that's right. There we go, R13. Yeah, looks good. Okay, so then we got a bunch of new words. Cool, let's take a look at these. Yeah, so we know this one isn't anything. So add it to our list of invalid words. And then F19C. We'll add this one too. Okay, those aren't in the list anymore. And then we've got an 84, 85, 85, 81. I think that's probably all the structure of it. So that's a move B, R0. Move B, R0 with displacement. So that must be this one. 8, 0, 8, 0. Yeah, okay. So 8, 0. And this is, that's weird. It's kind of like bundled with these other instructions. Huh. All right. Actually, yeah. Okay. So this is it's kind of good that I didn't factor this out yet, because it looks like it's actually got a completely different structure. But this is actually similar to like this one. And I think it's always MN. Says, I keep losing the things. I wish it would keep them highlighted. 8, 0, 8, 0. Yeah. Oh, I'm sorry. This is displacement. So this is like disp. And just to make sure what, yeah, the displacement is just a, it looks like it's just a 4-bit displacement, which is basically what we have. Okay, this is disp, this is M, no, N. Not like it makes a difference, but that was 8, 0, E4. Yeah. R0, 0, R14. Nope. Shouldn't be 0. I'm reading the wrong bits. Yeah, this should be that, and this should be that. R14.4. Nope, should be the other way around, right? Because this is 4R14. So we'll do it like that. Yeah, like that. There we go. 414. 414 move B. Yep. Cool. So there's our R5, and then got our 8, 1, E5. 8, 1, E5. Yeah, that's a move W of the same kind. So that would be, where'd it go? Move W down here. And it's an 8, 1, 8, 1, move W. Here it is. Displacement times 2. So just copy this. That's 1. And displacement is times 2. And we've got our move W. Okay, I want to add a little bit of color to this. Wonder how I can do that. Yeah, maybe I'll do it a little bit later. Because I think to do it, what I really want to do is actually factor out these into the instruction formats, and then once I do that, I can more easily tell like which parts of the instruction are which, right? So I could do that now. That actually might save a little bit of effort. Yeah, it might be more fun than just watching me fill out these tables. So what we do know is that there are certain instruction formats. Yeah, and they describe them here. So they call this like the 0 format, the N format, M format, NM format, and so on, right? And we've actually seen these. So if we look at here, this is like the NM format. That's why they call it that, right? It's basically the structure. This is NM disp. They probably call it NM, excuse me, NMD. That's this, I think. Yeah. So we can do is just say like have a function which is like format 0 and then the name of the operation, and then have that be what we call here. So instead of doing printf, we'll do format 0, and that'll do the printf for us. We can do the same one for here. And just to make sure that does the same thing, yeah. And so then this is format NM, and then we can do int n, int m, and pull this out here. And does this actually save us any? Maybe it doesn't, because what we'll end up having to do it looks like it's always mn, which is nice, but the m and the n can be like in weird places. So what that means is that we still have to keep the format here. So it's like, it's saving us doing the decoding, I suppose, if we pass in the instruction. So we can do it like this. Do we want to do instruction format? I think we do. So yeah. And then we'll call this format. And this will be funct. And so then just to try this out, we can do inster and then pass in this format string like that. Let's grep remove b to see if that actually worked. Yeah, that should be this one. Yeah. Okay, that worked. So this saves. I mean, it cleans up the code a little bit. What I'll do is I'll just drop in the proper instruction here. And this one's just a format n. Yeah. Which is like this guy. Yeah. So I'll just have this one printed out too, even though it isn't necessary. And so then format n always has it in this location, which is what we have. So pass the insert here. I'm actually kind of liking this. The other code was getting to be a little bit too ugly. Just make sure that compiles. And we'll look for our friend Mackle. See if we can find it. Yeah, that looks good. Cool. Okay. This is a nmdisp, so we'll write that one out. I'm going to say that this is always times 4 until we're shown otherwise. I'm not actually sure. It might be that that multiplication is different for different instructions. Yeah, it probably is actually. So we probably need to pass in the multiplier. That's fine though. So nmd. Yeah. So we'll call this mul. Like that. And the format is always disp on the left. So we'll do it like that. Oh no, it's not. That's annoying. Yeah, this is the problem with like the printf ordering, is that we can't actually. Yeah, so we'll just give it a different name. We'll probably want to do something smarter later, but for now this is fine. So in this case it'll be, we'll call this one MDN. Yeah, I don't know how I feel about this now. I'm already regretting this. I don't know, maybe not. And we'll call, well, actually, which one did we actually have here? This is mdispn, so yeah, that's an MDN. So until we find the other one, we'll have MDN for now. So this is format MDN of inster and this guy. Too few arguments. Oh, right, the multiplication. And that's move L. Oh, I don't actually. Well, we know it starts with 01, so we'll just look for 01. That didn't work. What am I doing wrong? It's like that. No. Oops. No. Oh no, it's not the. I want a word boundary. Yeah. There we go. Wait, where is it? Oh, it's not 01, it's 10. Yeah, there it is. Yeah. These ones all have the same structure. These are all NMs, so we can actually just change this to like this. Oops. And get rid of those and change this to inster. Now. Let's look for an and. Yeah. Alright, those look good. And these are also format and. So what's going to be cool about this is that once we sort of get the structure here, we can actually factor out pieces more easily. So like we can actually separate the instruction from the operands, and that'll let us do things like do coloring or whatever we want to do there. So that's kind of cool. This one looks like an N. I call it an M, but it's the same structure as an N, so I'll just do that. LCD. Looks good. good. Oh, so this one is disp mn, so I'm just gonna copy this and change the order like so. Yeah, this will make it nicer to add new instructions. This is Amigo. Yeah, so that's that one, I think. Nope. There we go. This one. Yeah, looks good. Yeah, there's a lot of these ones. Sometimes I wish there were faster ways to do this stuff. Like, it's always kind of a trade-off, you know? Like, you can go through and you can like try and parse the data out of the document, which would be kind of cool, but I do wonder how much effort it would take. Like, I don't know. I guess I'm spending like a couple hours doing this, so it really does. I don't know, just depends on what you want to do. Sometimes it's fun to write code like we did before, but sometimes it's nice to just, I don't know, I get kind of zen about it. Just like going through and just sort of staring at stuff and going, oh, okay, do this, okay, do that, you know? I don't know, maybe that's a little bit weird, but so this one's a different instruction format. This is add immediate, which has a 16-bit immediate at the bottom and a number. So this is an NI, so that's what we'll call it. We'll go down to this line here. Back up. Change this to font. Ooh. Yeah. Just make sure that one works. Whoops. Cool. Yeah. This one's looks like ND. ND8. This is ND and then the low bits. So that's like ND4, right? Yeah. Was that this one? No, that's this one here. There we go. So I'm just gonna copy that and move it up here. Like the rest. Change the format. There's our disp. Yeah, looks good. So this is format MD4. Mr. that. Just make sure that that actually builds. It does. Should be a move B. It should start with an 8. Yeah, okay, that looks good. This is looking good. Yeah. So this one's just an immediate. So that's this guy here. Yeah, the low 16 bits. And here's the low 16 bits. So we'll just call that format I. And grab that from here. We should probably do this split screen because it'll make it easier. I might switch to that in a second here. Yeah. So we had our value that we're saving here, but I feel pretty good about that. So we'll go back down here. Yeah. So this is our format I. Typing the codes. This one's interesting. This is our branch with displacement. Those ones probably are different. Like they call that. Yeah, they call that the D format. So call that D. And it looks like it's always the same, so the same multiplier value. So I'm just gonna leave that out for now, but we'll see if we need to change that. So this is font, and this is format D, and that's Mr. And like that. And this is the same. I'm actually kind of liking this. This is like, I was like regretting it, and then I was kind of liking it, and I don't know, I've kind of oscillated a little bit, but I think this is actually better. Return with value, so I need to return that there. I think this is actually like what we want. What did I do? 148. Oh, shouldn't be returning from that either. There we go. Yeah, I think this is I think this is going to be nicer. It's going to make it easier to just like copy one of these in. We don't have to like copy the structure. We just remember what type of instruction it is, and then we just write it out. So it's going to make it easier to add more of these. And you can also see that like if the structure is like really regular, we could actually even like factor it out maybe or something. Like when we actually start to make this into an emulator, we're going to want the decoding to be as fast as possible. Like that's going to be really important, especially for a RISC type architecture. One of the things about it is that like it's packing more bits in. Like if it's a CISC style, it'll usually be like the first byte tells you what type of opcode it is, or operation, and then the second byte tells you more information about it and so on. The RISC style instruction sets usually have like, you know, it's like what we're seeing here, like different types of structure. And so we want to make sure we can figure out like clever ways to optimize the decoding of that. So this is like starting to give some clues as to like how you might decode. decode the instructions in a fast way. Like right now, we can like get to say this instruction by basically masking off the top bits and then masking up the low bits and then checking a value. So it should be relatively fast. We'll see. We'll see. Like, I'm not too concerned about speed for now. Computers are fast, and I think this machine runs at like probably 20 megahertz. I don't think it's going to be super fast. So I'm not too concerned about us like just blowing speed in places. So this is format NDISP. I think we have one for that. ND. Oh, okay. So this is ND8. So we'll do this. Right? I think so. Disp N. Yeah, alright. I think that's right. What's probably going to happen is we're going to like realize that some of these are completely wrong, but this is mostly just to sort of get us the general idea of the structure so that we can start like piecing together what we're actually looking at. Right? Disp N, disp N. Oops, review. That's move review. Hey, Dario, good to see you, man. It's like we're like trading off EmuDev streams. Let's see. Move W. PC. Was that the one I was just looking at? 9.5. Yep. Yeah. Okay, and then this is branch with a, oh, so this is a bigger displacement. So we'll take a look at this one. This is a 12 displacement. So we'll call this D12. And copy that here. And then we can change this one to the format D12. And instruction. Like that. Oh, I missed this one. That's the same as this. So format D12. Even more obscure system to emulate. Yeah, I know, right? But that's kind of the whole point of this, actually, is that it is an obscure system, but like, you know, it's partially an obscure system because it's, you know, there's only 11 games for it or whatever, right? But it's also obscure because, you know, it was marketed towards girls in Japan, and, you know, part of the reason I got into emulators, honestly, is because, you know, it's nostalgia, right? And it's kind of sad that there's not really nostalgia around this type of thing. So, and maybe just because it was for girls, you know, or originally sort of made in that way. So I think it's kind of cool to, like, you know, yeah, show people that there is something there. You know, there are different systems out there. I don't know. Yeah, increase awareness. What is this? Is that this one? So this one's a sign extending, but this one isn't. Should this one have been? This is kind of annoying, actually, because I'm like second guessing myself with some of these. Yeah, so this one is not sign extending, and this one is sign extending. which is weird. It's like, does that mean that these formats don't specify whether or not it's a sign extending? Yeah, see, now I'm starting to regret this again. I've kind of like I've kind of like oscillated back and forth. A good number of people, including guys, who would be happy about this emu. Yeah, I think so. I think you're right. Well, I hope so anyway. Yeah. So I'm going to call this one sign D, and I'm going to call this one unsigned D. And this is our sign extending here, so I'm just going to change this to not sign extending, which we can just leave like this. So then we'll do this. I have to say, like, it's so funny when you watch people stream, you're like, oh, that looks so easy, I can totally do that. And then you do it and you're like, ah, oh, this is hard. It's like, it's fun, but it's like, you know, it's not easy. So yeah, major props to streamers, because you're like coding in front of everybody, and like, I feel like a pretty confident coder, but sometimes I'm just like, oh man, everybody is like watching my every mistake and like looking at me and just shaking their head, right? So I'm gonna want a multiplier for this. So this one is a 2. Ooh. How did I break this one? Oh, this. I think this one I don't need a multiplier for. You do gain confidence. All right, good to know. I'm trusting you that it gets easier. Oh, does that mean I got through all of these? I think so. This one is... Yeah, I think what might happen is kind of like these initial streams, it's like, it's kind of, you're like, oh, cool, streaming stuff, but it's like so much setup work. And I bet that like once I start to have like more functionality there, it's going to be way more fun, because it's going to be the stuff where it's like, oh, what are we going to work on? I know, I'm just going to, like, I don't know, hack some stuff together. Or like, I want to play around with, like, one thing that I was really excited about was doing a reverse debugger. I thought that would be really cool. Because, like, actually, when I was watching your stream, Daro, how do you say that, Daro? Anyway, I was watching your stream and I was like, you were doing this thing where you were like trying to figure out like why a value changed, and I was thinking, like, if you could do reverse debugging, which is like a real thing, it would be so awesome, because you could just basically set a breakpoint and then run backwards until the place where the breakpoint is hit, which would be like, don't worry about it being fun. No, I definitely know that it's not going to be fun for everybody. That's true. Also, most people watching do not think what you're doing is easy, believe me. Huh. Yeah, no, I think you're probably right. Oh, but like I was saying, I think it'd be so cool to be able to do, like, reverse debugging, to be able to track this kind of stuff down. And I know for my Game Boy emulator, I really wanted to add something like that. So I think those types of things could be really cool. It's not really helping you actually solve the problem of, you know, actually running games and stuff, but it will make it a lot easier when I'm actually trying to track down issues. So this is ndisp times 4. This is nd12, nd8 times 4. Yeah, so I need a multiplier here. I love assembly, and a lot of this is still beyond me. It's super fun to watch, though. Oh, thanks for saying that. I honestly, if there's stuff I can maybe explain better, I'm happy to try. I know it's like kind of weird. There you go. Yeah, I mean, I know, like, I guess I'm used to writing a lot of assembly, and so this stuff maybe gotta be Browns. What is Browns? So maybe this stuff like makes a little bit more sense to me, but honestly, I'm learning all of this as well. So, or reds, MX blues. Oh, my switches. Yeah. This is a. Can you see it? I don't know. I can't actually tell if. And of course there's a delay, so now I'm just going to be holding it for a second. I feel dumb. Okay. Yeah, it's a Corsair. I think these are Cherry MX Reds or something. I don't know. Are they too loud? You're all like, shut up your stupid keyboard. What am I doing? This is ND8. No, so great. Yeah, seriously, I was typing on like this crappy Microsoft, I don't know, one of the giant Microsoft keyboards, and I was like, I'm gonna get a real keyboard. And I did. Is that right? What did I do? What am I doing? Oh, no, this is a different one. This one was times 2. Of course it's times 2. It's because it's a move W, word sized, 2 bytes. Can't stick around past midnight, but I want to say hi and cheer you on. Totally. Thank you so much. I really appreciate it. Yeah. Us MU devs gotta stick together, right? All the best. Thanks, man. Yeah. Oh, okay, wait. What is this one? This one's a move immediate. So this is like move. Yeah, so this one and this one are the same, but the immediate is sign extended. So, okay. I need to do like, this is sign extended immediate, and this is unsigned. Yeah, this is getting a little bit more complicated than I wanted it to be. I kind of went down this path because I thought I was going to make it everything better, and now I just don't know. That's okay. This is like early code. Okay. NI. Oh, okay, right. I have to change that other one to NUI. Okay. 85E1. Oh, yeah, okay. So, if I was smart, before I did all this refactoring, I would have saved off what the output was, because now I have no idea if I just broke everything. Oh man. Alright. Well, I'm gonna save off what I have now anyway. So I'll call this refactor.text. Alright, well, so can go back over this later and see if I made any mistakes. I'm sure I did. I'm sure I did. And actually, if I was smart, I could have done like saved it off in Git. so that I can just do a git diff instead of having to do like a textual diff or whatever. But, you know, that's how these things are. Okay, right. So 85E1. Back to where we were before. There's our move W with displacement. But so the cool thing is that now we should be able to add these real fast, right? We'll see. So this is 85E1. I'll go back to move W with displacement. On this side, that's, where is it? Move W with displacement. Move W with displacement. It's got to be this one. 85. Yeah, that's the one. Okay. And it's ×2 with sign extension. Do we even have that one? We don't. Damn it. Ah. Okay, so what we want is one that's like this one with sign displacement or sign extension. So now this is this, and this is this, and then this gets sign extended. No. Okay, wait. No. The sign extension happens on the value that gets read. It does not sign extend the address or the displacement. So it means we can use format ND8. Yeah, this this was a bad refactor. I shouldn't have done this. All right, well, you learn. Right, so here's our 8.5. There's our 8.5. We know this is an ND8, and it's a move W displacement RM R0. So that's displacement RM R0. And it's multiplied by 2. And that's a move W. 450? 2. Yeah. 85E1. Oh, it's an ND4. Which makes sense because that's an ND4 as well. And of course now I'm getting too many arguments to ND4. So this should actually be mul, and that should be mul, and then it's going to barf on these guys, which makes sense. This is probably supposed to be like that. Okay. There's our 85, and it's 2 with R14. 2 R14. Okay. All right. Yes. See, it's making everything better. Everything better. All right. Back to our regularly scheduled program. 30C4. So I'm probably going to stream for maybe another 20 minutes unless something something fun happens. Just trying to get through this stuff here. So 30C4, 30C4. So this is kind of a fun instruction. This is a div1. Ourselves a divide. Single step division. What does that mean? All right. So that's a 4. Is that right? 4? No, sorry, 3, 4. 3, 4. Yeah. There's our 4, and we know that this is format NM. We can just change that to that. And there we go. All right. What do we blow up on now? 31AE. 31AE. Add C. 31AE. Add C. Let's just make sure that's what we assume. Yep. All right. Here. There it is. Cool. R10, R0. Yep. All right. What are we blowing up on now? 3237. Comp GT. So I already saw some other comps. So let's see. 3237. 3237. So that'll be 7 here. GT. Let's just take a look and make sure that's right. Comp GT 37. Yep. And there's our comp GT. Okay, what are we blowing up on now? We have our 46C2 here. Let's try that out. Nothing. So we can add that to our list of invalid. 46C2, is that right? 46C2, yep. Okay, and then, oh, you know what? End. Yes. Got through the instructions. Okay. That's pretty great. I feel good about this. Yeah. This is very cool. Yeah. All right. Should I bump up the limit, or should I do something fun like? Yeah, I want to add color. I was planning to do that before, and I want to add it. So now that we have all these instructions that are separated out into this structure, it makes it super easy to do. If we actually if we separate out the funct part, which is the operands, from the operator, so we can do this. This will all break now. Actually, I probably should have checked that in. Oh well, it'll be fine. What could go wrong? And I know that I want to, let's see, how do I want to do this? It's like the op has to go first, but I want to basically not have to include it directly. So what I'm going to do is I'm going to have like a separate format. Is that how I'm going to do it? I have a separate format function that you pass in. Basically what I'm thinking is I want to separate this part out like this. And then have it build up the components separately. Oh, you know what it is? Yeah, I don't even, I can just do print op. And then we'll do this and op, and then we can pick a color. So let's make it green. So that's this bit of goop here. Like that. And then you can go back to white. That's this bit of goop here. Yeah. And then we can change this to print op, and then print op, and so on. I just want to see what this looks like. Okay, right. So then it's going to break a bunch of stuff, but that's fine, because we'll just go through and fix it. So, oh, yeah, op is the format in this case. Yep. And then this just has to be like that. And it's going to be the same for all of these, like this. Maybe what we want to do in the future is actually structure these up so that we can have sort of like a generic decode, and then once we've actually decoded it, then we can sort of decide what we want to do with the values. Like, we'll know certain values are registers and certain values are memory addresses and so on, and we can sort of do what we want with the structures there. I'm not going to introduce too much additional complexity. I mean, this is just a, like, we can sort of see some nice stuff here. But it does mean that we could actually do neat things like highlight registers differently than memory addresses and so on, which, again, probably nice. Especially because we're going to be looking at this stuff a lot, you know, make it look nice. And honestly, I probably wouldn't have done this if it wasn't for the fact that, like, yeah, okay, that kind of looks like something. I wouldn't have done this if it wasn't for the fact that Daro, who's working on Vectrexy, did the same thing. And I was like, oh, you know, actually it looks really nice with colors. So, yeah. I don't know, it's kind of cool, I guess. Let's put these up at the top. In fact, let's just grab a bunch of these colors. cool. Now we can do stuff like this. We can make this red, and then make this white. Yeah. I don't know if red is the right color, but I don't know. It's kind of cool. Looks like Christmas. Or was that the Italian flag? Maybe. Okay. Yeah. Cool. All right. So should I do more? Oh, well, actually, one thing I can change here is this is how much we've looked at, right? But currently, we've looked at a lot more than that. So we can change this to C7E. Actually, do we need looked at anymore? We were using looked at to determine which ones we had already looked at, but we basically already did that. So I'm going to get rid of looked at, actually, because now we just need words. Oh, and, well, we could highlight word. I don't know. Actually, it might be nice to change word to a different color so we can see the stuff that's like clearly invalid. So we'll change that to, I don't know, magenta. Magenta is like pretty aggressive, but yeah, actually that's not too bad, right? I'm actually kind of happy I did this. I like this. I don't know. I think it's kind of cool, actually. We're probably going to want something a little bit nicer than this eventually, but like for now, this actually is making it, you know, adding a little color to our lives. All right, so should I clean up a little bit before, like I said, I'm probably going to stop at 10. I don't want these streams to be too long, you know. What can we clean up and just make a little bit nicer so that we can continue on later? I still like print words. I like our little formats here. Well, one thing is we may want to have the color on a flag, because as it is currently, I think if I do like this, we're going to end up with, yeah, see this, there's all this garbage in here. These are the actual color symbols that it prints out. So we might just want to say like, use color 1, if use color, do this, otherwise do this. And we probably don't want it on a flag, or on a define, but it's fine for now. Will that work? Maybe. Let's try it. Yeah, that's good. All right, get rid of that. All right. Yeah. Okay, now I'm a little bit curious. Like, what I could do is, rather than asserting, I can have it just do like G words and basically add them all up. Then I can have the same list for everything, which, like, why not, right? So instead of doing this, right, I can, whoops, nope, I didn't want to do that either. I'm going to turn this back on, and I want to do this, and I want to run, right? So just say I bump this up. Yeah, see? So now it's actually accumulating all the different words that I haven't seen yet. And like I could bump this up to that, right? Oh god. Okay. I'm not gonna do that many. But who knows? Maybe a lot of these are maybe a lot of these are not valid? I don't know. Okay, well, I want to just do a couple more. I can at least do this. Actually, I guess I can still do what I did before and just like straight up copy it in here and just see. Yeah, so some of these are actually, whoops, what is going on? Some of these are actual, no, none of these are. Yeah, okay, cool. So then this is the cool thing about this, is that now, rather than having to like check them individually, I can like literally just, I can just do this and like, yeah, it makes it so it's much easier to bump these up. So like, even if I do that, then I can just grab this list and drop it in. Oh, come on. All of these are instructions? Yeah. But this one isn't. So, you know. It gives me a clue as to which ones I actually have to implement. You know? And I think what will happen is that a lot of these will actually be like the same instruction, right? So like these two are the same, these two are the same, and so on. So it'll you know, it's not going to be like 2,000 instructions, you know? But yeah. Okay, I'm pretty happy with this. So let's just go back over what's been done here. Added the colors, added this invalid list, added the formatting of instructions, which probably has bugs in it, but it's close enough. Switched all these decoders over to use the formatting instructions. Yeah, and then disassembled 2K. Not bad for a couple hours work. Not bad at all. Alright, I'm gonna check this in. Added colors, more instructions. This way, when start streaming next time, we can diff and see the progress. So I'm going to call it a day. Thanks for watching, folks, and I'll see you next time.